Good afternoon, everybody. Phil Green again, Technical Solutions Director at Saint-Gobain PAM. This is the latest in a series of presentations. Today we're going to talk about the anchorage of ductile iron pipes and talk through some of the issues that might present. So basically, correct anchorage is essential to any pressurized pipeline. So the object of today's discussion or presentation is to try and improve the understanding of how ductile iron pipelines might be anchored, and how and where anchorage should be used. Perhaps talk about some of the theory behind anchorage and calculation processes for anchorage, and then look at different types of joint systems which offer self-anchorage, and then at the end we'll touch on a computer program that we have that enables us to understand anchorage requirements on a project. So this is all about how we might restrain push-fit pipes and anchor push-fit systems. So pressure pipelines with push-fit flexible joints are subject to forces at changes in direction. On a push-fit system, this can tend to separate the joints at changes of direction, where you've got blank ends and tapers. So at these locations, some form of restraint might be required. Not always, but might be required depending on the pressure and the ground systems. So on the little diagram you have here, so you've got bends, you've got T's, you've got angle branches, blank ends, tapers, etc. All of those generate thrusts or generate thrusts in a pipeline. So these thrusts need to be understood and controlled to retain a push-fit system. Unless, of course, pipelines are laid in a dead straight line. There's an example here of a pipeline. This is in Abu Dhabi, which Martin Addison knows a lot about, which is a long straight pipeline. So where there are no bends or T's or changes in direction, there'll be no sideways thrusts to encounter. So long straight pipelines often don't require anchorage. As I mentioned, it's just about when you come into changes in direction or changes in pipe size or any other introduction of a fitting into a pipeline is where you might need anchored systems. Excuse me. So to understand thrust forces, pressure within a pipeline produces thrust forces, as I mentioned earlier, changes of direction or changes in cross-sectional areas. These thrust forces need to be firstly understood and then restrained by the soil and/or with thrust blocks or a self-anchoring system. And thrust forces arise due to internal hydraulic pressure acting upon a cross-sectional area of a pipe. And a direction of the thrust depends upon the shape and orientation of the fitting. So as you can see there, thrust forces are calculated by the pipeline pressure by cross-sectional area, and that can be different depending upon the direction and shape of the fitting in a pipeline. So you could have bends, angles, T's, etc., tapers, where you'll get production of thrust forces that will need to be understood. So as I say, any change in direction, you need to understand that. I guess to try and understand or put some context to the proportions of thrust, is an example here of an 1800 millimeter diameter pipeline. This was a PAM export project in Algeria, and at the bend you can see in this particular photograph here, if it's pressurized to 16 bar, you're generating a thrust of over 200 tons at the bend when it's pressurized to 16 bar. And the thrust on a blank end on this particular pipeline at 16 bar would be 830 tons. So that gives you some kind of order of magnitude in terms of thrusts that you can generate as you get through the pipe sizes in a buried pipeline. But even at 100 millimeters, a 100 millimeter pipe would develop about 1/3 of a ton of lateral thrust, and over 1 ton of thrust of end thrust at 16 bar. So I guess we've gone to the extreme to demonstrate the point, but even in small diameters, on a blank end at 100 millimeters at 16 bar, you still generate over a ton of thrust. So it's certainly significant and needs to be considered. A little bit about anchorage theory. The theory is based upon equating the various forces that act on a buried and pressurized pipeline or fitting, using various safety factors. Now, these forces can be described as the force produced at a change in direction caused by the internal pressure, the passive force of the soil resisting the movement of the fitting, the frictional and cohesive force of the soil resisting movement along the anchored length of the pipeline, and the passive force of the soil against the anchored joints resisting movement. So in theory there, we've got a force that the pressure pipeline produces, and then you've got, if you like, resistance forces of the soil and the surrounding area and the cohesion of that soil on the pipeline. So it's to understand the relationship and the mechanism between the force that's generated and the natural resistance of the soils and the ground cover that you've got, and understanding how you might need to supplement that resistance by anchored systems. So the calculation of the length of a pipeline or number of joints requiring self-anchorage is based upon the concept of ensuring that you've got a combination of the anchoring conditions of the soil restraint and the self-anchoring forces that you need to exceed the thrusts that you can generate at any point in the pipeline. So, as I say, it's based upon the concept of understanding and ensuring you have a combination of resistance to overcome the force that you're generating. So, some of that resistance, as I mentioned, comes from soil forces. So, passive soil resistance, you get that at bends and tees, etc. You get passive soil resistance of the pipe adjoining the fittings. You get passive soil resistance of the sockets of the pipe, because pipes and fittings, they have a socket on there, therefore the profile of the pipe at the socket end, as that's trying to move through the soil, that will create some resistance of the socket movement through the soil. And then you get frictional and cohesive conditions within the soil, which will resist movement of that pipe. And depending on the type of soil that you've got different levels of friction and cohesion within different types of soils. So all these resistance are functions of the depth of cover, the soil density, the soil cohesion, and height of water table, etc. Because if you're in a very dry situation, they'll probably get more friction, because the soil tends to stick to the pipe more. If you've got a water table, generally that acts as, if you like, a lubricant of the soil between the pipe and the surrounding soils. So it'll reduce that friction. Therefore, you might need to anchor a longer length if there's presence of a water table. So passive soil resistance is created as the fitting of the pipe tries to move through the backfill and the soil combination. And there's a theory around this called Rankine's theory. And basically, Rankine's theory considers that the soil is to be in a state of plastic equilibrium, and makes some assumptions that the soil is homogeneous, isotropic, and has some internal friction. And the resistance offered by the soil to an object pushing against it is referred to as passive resistance. So that's just the passive resistance of the soil in the ground. So there's a theory behind that, and that's what that theory is built up on, to create that understanding of passive resistance. You've then got frictional cohesive forces. So these are frictional cohesive soil resistance is created as the pipe tries to slide actually through the backfill or the soil combination. There's another theory around this, which is called Coulomb's theory. And Coulomb's theory suggests that the resistance is the sum of the frictional force and the cohesive forces. So Fp equals Fc plus Ff. The cohesive force Fc, is given by pi d multiplied by the cohesion efficient of the soil, and the frictional force Ff is given by pi times diameter multiplied by the product of the average radial pressure and the soil friction coefficient. So there's lots of factors in there that we need to understand, which is to do with soil mechanics. But if you understand the soil mechanics, you can apply those soil mechanic figures to the anchorage system, anchorage calculation, to define the system that you might need and the total length of anchorage in a pipeline. All sounds quite complicated, as I mentioned earlier, but there are programs we can look at that simplify this process and take all these forces into consideration and use different specific soil conditions to enable us to understand what a condition might be for anchorage. So just to talk about how we calculate thrust, we've got thrust at a blank end or a valve. And as you can see there, the pressure thrust in a push fit pipeline is determined using the external diameter of the pipe, which is reference D on here, because the pressure acts upon the end of the spigot, and in the case of valves, it is usual to assume that the pressure can act in both directions, i.e. you're going to need anchorage on both sides of a valve. If it's a blank end, of course, you just work back from the blank end. If there's a valve in a system, it's often necessary to have anchorage moving away from a valve in both directions, just to mitigate that thrust in both directions. Then we'll look at thrust at tapers, and at a taper, the thrust is assumed to be the product of the pressure and the effective cross-sectional area. So what you've got there is a subtraction of the cross-sectional area multiplied by the pressure divided by 4. That gives you what your thrust might be. So again, there's a calculation that's quite straightforward to understand what that thrust would be on a particular taper. And there's various, obviously, calculations for different cross sections of tapers and T's and bends or whatever it might be. Moving on, we talked about friction and cohesion earlier. So friction and cohesion in soils, which we reference FP, acts upon the barrels of anchored pipes to oppose the pressure thrust. There will also be passive soil forces acting on the anchored sockets and a small amount of passive backfill resistance. Some of those passive resistances are small, but they all contribute and are included in analysis. And in this particular slide, I've omitted the forces at the socket for clarity, but where you have got sockets there, you will get some resistance at the face of those sockets as well when that's trying to move through the soil. So all of those resistance forces are calculated, accumulated as part of the calculation. And as I mentioned earlier, depending upon the soil types, the friction and cohesion forces will be different depending on, as I mentioned, whether the soil's stiff, firm, or soft, and water table present. Then got a thruster to T. So to understand a little bit more about the thruster to T, it's the product of the pressure and the cross-sectional area of the branch pipeline. So that's how we calculate pressure at a pressure thruster to T. And the way that manifests itself, the force acting upon a pressurized pipeline at a T act similarly. The T and the two adjoining pipes will develop passive resistance at the top of that slide there, which is classed as FR, which is passive resistance. So there'll be a resistance to the soil trying to move that fitting and those pipes through the soil, and as they try to move laterally through the backfill. The passive resistance FS will be developed as the sockets try to force their way through the backfill soil, and the frictional and cohesion forces FP will try to restrain the actual movement of the pipes sliding through the soil there. And often there's no need to anchor joints in the main. So where you've got the T section at the top and pipes in the main, often there's no need to anchor joints in the main because the joint deflections adjacent to the fitting are so small. It's just the movement actually down the branch that tends to be considered, so they don't pull those joints out and get a problem with those particular joints. Understanding the pressure thruster to bend. The thrust is the product of the pressure and the cross-sectional area resolved in the direction shown. So depending upon the angle of the bend, there's a calculation that can define what that thrust is going to be at that particular angle. And obviously it can have a 45, 22, 11, or even a 90-degree bend. So obviously you input those dimensions or those angles into that calculation to end up with the thrust calculation. Now, when you're looking at pressure thrust on a bend, the pressure thrust is shown in black arrows on the diagram that we have there. And you can replace this by two forces at right angles shown in green. And these forces are known as vectors, which is a force with a direction. And the green, if you like, the vector forces form a right angle triangle with the black forces. And the green forces produce the same thrust as the replaced black forces in that particular diagram. So you've basically created a vector diagram there of the thrusts that you're generating. So the addition of the two sets of green forces give you, if you like, give you 0 in the horizontal direction, because those two forces cancel each other out in the horizontal direction. But what you'll get there is a pressure thrust in the vertical plane. So that's the theory behind how we calculate that thrust, and how pressures in the horizontal section neutralize themselves, and the vertical sections are, if you like, calculated and almost doubled through a vector diagram. The way this manifests itself is a soil reaction at a bend. So you've got the diagram here, which shows the soil reaction acting upon a pressurized pipeline at a bend are shown. The bend and the two adjoining pipes will develop passive resistance, again reference of FR, as they try to move laterally through the backfill soil, and then passive resistance, FS, will be developed as the sockets try to force their way through the backfill, and frictional cohesion resistance, FP, will try to restrain the actual movements of the sliding pipe. So all these things, all these forces work together to try and mitigate the thrust in a pipeline. And if you've got good ground and low pressure, often that can be the case, that the ground itself will restrain the thrust. If the thrust is exceeding the resistance, then you have to think about an anchorage system, which we'll come on to later in a more detailed calculation. Excuse me. We've then got thrusts at an angle branch, and again, there's a calculation that defines what that thrust is, or how you calculate that thrust, and it's the product of the pressure and the cross-sectional area of the branch pipeline. However, the thrust is in the direction of the angled branch, so you've got an unequal thrust there. So when we spoke about a vector diagram earlier, it's a slightly different vector diagram in that you've got an unequal thrust, which is the direction of the angled branch. And again, just to show what this looks like in a pipeline system as a diagram, what you've got there then is the movement of the fitting, which generates passive soil forces, again FR, around the fitting and the adjacent pipes. In addition, the angle branch pipe mobilizes friction and cohesive forces FP, and the angle branch behaves as a hybrid between a T and a bend. So anchorage might be needed in this case in the bend, because it's pulling on the bend as well as pulling on the branch. So in this instance, you might need anchorage down the main to the left there of where the angle branch is, because it's trying to move horizontally up to the right, rather than vertically up and horizontally across as a uniform load. But again, just illustrates where the resistance forces come into play and what you need to consider as part of that calculation. So when you review that, we can see that pressure pipelines having push fit flexible joints are often subject to forces, and these forces, because it's push fit, can tend to try and separate. So the outcome of that those thrusts can be that if that thrust's too great, you can separate the joints, i.e. you can pull the spigot out of the socket, where you've got those changes in directions. So at these locations, some form of restraint might be necessary. And in simple and more traditional terms, these forces can be restrained using concrete thrust blocks. So what would normally happen, or what can sometimes happen, concrete thrust blocks can be put in place behind changes in direction. And that will be a simple method of anchoring that particular system. And there's a report in the UK. I don't know, forgive me, but I don't know what the guidance is in Ireland. But in the UK, there's a report called Syria 128, which is the guide to the design of thrust blocks for buried pressure pipelines, and that's what's used to understand how thrust blocks might need to be designed. The challenge with thrust blocks is that in Syria 128 guide, they take very little account of soil resistance. It's almost like the pipeline is, for want of a better term, it's in fresh air, so the concrete has to restrain the whole of that thrust. And that can sometimes lead to huge requirements for concrete thrust blocks, which are sometimes quite impractical depending upon other services or depths of cover or reuse of land that you're putting a pipeline in. And moving forward as well, there's also a consideration for embodied carbon within concrete. So each cubic meter of thrust block that's designed is equivalent, I think it's approximately 200 kilograms of embodied carbon dioxide per 1 cubic meter of concrete. So there's a huge consideration there about embodied carbon and reducing embodied carbon. So thrust blocks can be used. But with this sustainability agenda that's I think on all of our minds, it's how do we reduce the embodied carbon within that design to try and mitigate the use of concrete. Now, if you can't use if you can't mitigate the use of concrete, you do need to use concrete thrust blocks. This diagram gives an illustration of where concrete thrust blocks can be used. And it's very much the same as Saint-Gobain PAM anchored systems. You can use them at horizontal bends. You can use them at blank ends. You can use them behind T's. You can use them to mitigate vertical thrusts on buried pipelines. And you can use them where you've got a gradient and a thrust developed through a gradient. So the traditional means of using concrete thrust blocks can still be done. But what we have solutions for is instead of concrete thrust blocks, we can provide anchored joint systems, and we have a range of anchored systems that we'll go through later. But what I'm saying is there's an alternative to concrete that we can introduce to pipelines that will enhance your sustainability score by mitigating embodied carbon in your designs. So to understand what the calculations are, how we understand the number of anchor joints required, there's a few sort of guidance notes. Where you've got pipelines above ground, which may be on plinths or whatever, because there's no passive soil resistance to those, and often all joints might need to be anchored. And the use of, as I say, anchor joints is an alternative to traditional anchor blocks. And obviously, where you've got very soft or unstable ground, or where there's little space due to existing surfaces or steep slopes, you can use these anchored systems. So to satisfactorily achieve anchorage using self-anchored systems, it's rarely sufficient to anchor the fitting alone, since this will only move the location or possible separation further down the pipeline. So although it's not normally necessary to anchor all buried joints, we need to do the calculation to understand how many joints away from a bend you might need to anchor to mitigate the thrust. So as I mentioned there, if it's above ground, all joints might need to be anchored. If it's buried, rarely all joints need to be anchored, but you need to do a calculation to understand it. And that calculation will give us if you like, the number of anchored joints that will be developed from away from a bend. And it can be quite complex. And it's not proportional to the internal pressure. So if you had, say, 5 meters of anchorage for 5 bar, it wouldn't be 10 meters of anchorage for 10 bar. It would be, there's a quite complex calculation to that. So it's not linear, it's not binary. It's unique to each particular situation that you have. So it can be quite complex. As I mentioned earlier, we have a calculation or a piece of software that we can use to help understand and define what that anchorage requirement might be. So I'm going to go through a sort of example of a calculation. So when calculating anchored length or the number of anchored joints required, it's normal to apply a factor of safety of 2 to the working pressure and 1.5 to the test pressure, and the pressure to be restrained, P, is the greater of those two parameters. So it's either 2 times the working pressure or 1.5 times the test pressure. Whichever is the greater of the two is the pressure that we use as part of the calculation. In the case of a bend, the resultant thrust is half the diameter. Well, I'm not going to read the calculation full, but you can see what the calculation is there for, where theta is the omega, is it L theta? I can't remember which one it is now. Is the angle of the bend, and the restraining forces acting on the bend are resolved in the direction of thrust. So you can see that from that calculation there. You've got various calculations which are resolved in the direction of thrust within a particular pipeline arrangement. So that's how those anchored lengths or those anchored requirements are calculated. or how they're understood, should I say. So from those calculations, there's a set of parameters that we then apply to that to understand the amount of anchorage that might be required. So if twice the passive backfill resistance resolved in the direction of the thrust is greater than the thrust, then no anchorage is required. So basically, we've got enough residual thrust restraint from the soil, the depth of cover, and the passive resistance of the soil in the ground. And often that can be very stiff clays, very low pressure, very small diameter. Generally, you can get away, if that's the right word, you can get away with no anchorage. However, if twice the passive backfill resistance plus the frictional and cohesion of soil restraint forces on the cut pipe resolved in the direction of the thrust is greater than the thrust, then only the bend needs to be anchored. So there's a bit of a calculation through there to understand if 2 times that requirement is equal to or greater, then only the bends need to be anchored. And if the thrust is greater than the second value, then the anchored length is given by the equation shown there. And basically what that takes in there is a length of cut pipe, length of bend, plus a number of parameters for total length that requires to be anchored. And again, it can be quite complex, but we have a calculation tool that defines and configures what that requirement might be. But all of this is just to give an understanding of the logic behind the calculation. Now, as I mentioned earlier, we have a calculation tool called, well, it's called PipeSpec. I've not mentioned that. We have a calculation tool called PipeSpec where you can carry out anchored length calculations. We've also got a PDF of the longhand calculation methods, because often if we share outcomes with an engineer or a designer, they'll say, that's great, but I need to see the longhand version of that so I understand the mechanics behind it. So again, we've got longhand calculation PDFs of all this. So if you really want to, you can work through that yourselves with a longhand calculation using the PDF as a guidance, but it's a lot easier and quicker to use the PipeSpec software that we have. So that's how anchored length is calculated, and the various rules that define what the anchored length might be. And of course, the greater the pressure in a pipeline, often the longer the anchored length. So this is very much dependent on pressure, soil, depth of cover, and type of soil, as we mentioned earlier. So once you've calculated the anchorage, I guess it's useful to understand the types of anchored joints that are available. And from a Saint-Gobain PAM perspective, I'm going to talk to a few of our anchored systems that are available now. So as I say, you can use thrust blocks if you want to use thrust blocks. If you don't want to use thrust blocks, there are alternative solutions available. So the first one we'll look at is what we call the rapid anchor joint. And basically what this is, what we've got here is a cross section of a pipe and a fitting. Excuse me a moment. So what you've got there shown here, you've got the socket and the spigot connection. The gasket there is shown in black, which is for water is an EPDM rubber, and then within that rubber there are anchors, stainless steel anchor teeth, which sit within that rubber, and they bite into the outside of the spigot. So basically, the red element is a stainless steel anchor tooth which sits inside the gasket. So when you make the joint, that bites into the spigot to stop that spigot pulling apart, and grips the spigot tightly to, as I say, to prevent withdrawal, actual withdrawal. So basically, the pressure capability of these joints is listed there, and it's generally compatible with the majority of water supply operations, which tend to be between 6 and 9 bar. And also, this joint is also capable of radial deflection. So there's up to 5 degrees of deflection in this joint, excuse me, depending on the size of the pipe. So at small diameter, quite high pressure system. As you get through the size range and it becomes bigger, the pressure capability reduces slightly, because the greater the diameter, the more anchor teeth are required. So we downgrade the pressure requirements to ensure that we don't overstress the gasket and the joints. We've listed up to 600 on this particular table, but it's also available in 700 as well at 10 bar. So quite a broad range of solutions there for general conditions. Now, if you wanted to go higher than the pressures, when you get to sort of 350 and above, if you wanted to go higher than 16 bar or 13 bar, 11 and 10, we've got what we call the HPVI system, which is basically takes you to the next pressure class up of pipeline. So you can go from a C25 to a C30 or a C30 to a C40. And if that's the case, it increases the pressure capability of this particular joint. So that's what we call our standard anchored offer. We've then got what we call mechanical anchor system. And this is, if you like, the more traditional double chambered system that we have. This is generally being phased out now because we've got other solutions that are better than this. But mechanical anchor, you might have pipelines in the ground that are jointed by the mechanical anchored system. And basically what you've got here is a weld bead, a circlip inside the weld bead, a gland and bolts which are hooked over the spigot end of the pipe or the socket, pulled through so that it can be tightened up and act as a ball joint. And what you get there is the circlip sits behind the weld bead inside the gland and stops the whole thing pulling apart. So you've got that sort of double angled resistance there that the circlip hits on the internal angle of the gland and stops the thing moving around. And again, you can see the size range available there and the pressure ratings available there. And again, there's also up to 5 degrees of flexibility within this particular joint. So there is some allowance for settlement on site and deviation on a pipeline if you need to use that for use some of that angular deflection to deviate along a pipeline. For large diameters, we've got what we call the PAMLOCK joint. This is available in 14, 1600 and 1800 pipe diameters. This is quite a specialized joint. It's got a segmented locking ring. It still uses a weld bead on the spigot end of the pipe, but it's got a segmented locking ring, and then it's got like an internal clip that sits behind that locking ring. And what you can see behind that red clip there is that there's an annulus in there which is basically filled with shot to complete the joint. And what that shot does, it fills the annulus, stops the red locking ring moving around, and prevents the whole thing coming out of the joint. And then that's locked off with a seal to prevent the shot escaping from that void. So the whole thing still works as a ball joint, but it can be quite complicated to joint. So it does need some time to make each joint, but it does the job and it's capable of the pressure ratings that you can see there. Now, a lot of the challenge of these are that they can be quite fiddly to join. So what we've also got is a range of other systems called double chambered locking systems called the universal range. So basically, the universal range is a double chambered joint. In the first chamber to the right there, you can see the gasket, which affects the seal, stops water escaping, gives you the pressure capability that you're looking for there of 60 bar at 80 up to 16 bar at 600. And in the second chamber, you've got what we call a carrier gasket with anchor teeth in it. And what happens there is that carrier gasket sits in that second chamber where the red anchor teeth are, locates into the outside of the pipe, and again locates into that angled section to engage in that angled section and stop the thing pulling apart. So you've still got that engagement of teeth in the spigot end of a pipe to stop the thing pulling apart. And that's what we call our universal VI joint. As a derivative of this and an addition to this, we've got what we call our universal VE locked joint. Now, this uses the same pipe profile. So you look at the same, you've got the same pipe profile as you have with the gasket version. You've got a double chamber in the in the socket end of a pipe. And the water seal is made in exactly the same way. You've got the black gasket there that affects the seal, stops the water escaping. In the second chamber, you've got what we call the locking ring, and the red semicircular piece there is a weld bead on the outside of the spigot, and all those things work together to weld bead locates on the red locking ring locates on the inside of the second chamber, and again stops the whole thing pulling apart actually. As you can see on this particular joint, it's capable of much higher pressures than the anchored systems, because this is a physically locked joint, so the pressure capabilities of this are higher. Now on this particular slide, it illustrates that the highest size is 1200. We've actually developed this further now, where it's available in 1400 and 1600 at 20 bar. So again, big pressure, big diameters. We've got a solution for that, and that solution then mitigates the need for the PAMLOCK joint that I showed earlier, because this is an easier to a joint system. And the benefit of this joint, and the previous one I showed you, is it's boltless, so you don't have to go down the trench, you don't have to fasten bolts up, you've not got a guy down there fastening and torquing bolts up to an agreed requirement. It's a locking ring, and there are wedges to enable you to joint that correctly, and a method of installation, so that you can take the clips out. The locking ring then grips on the pipe and locates behind the well bead to create the locked system. Another couple of derivatives that we got. There's one here called the V&I joint. We tend not to use this. It's a combination of the gland piece and the anchor gasket carrier. This tends to be used in France a lot, but certainly not in the UK. But it's just something to illustrate that there's another alternative, but it's not well used, certainly not in the UK and Ireland. Moving on from that, excuse me, we've got flange joints. So far we've looked at anchored systems, which have a degree of flexibility, and the whole point of those anchored systems is you can still have ground settlement, though they can still accommodate ground settlement. You've still got up to 5 degrees of angular deflection in those joints to mitigate ground settlement. When you look at flange joints, these joints have flat mating surfaces and they're bolted together, and the pressure is retained by the gasket between the faces. So with flange joints, you don't have any flexibility. Now the diagram we're showing here is a fabricated flanged pipe joint. Some of you may be familiar with this because we manufacture these in our facility in the UK. What we do is we have cast flanges. We machine the flanges to suit the outside diameter of the pipe. We then heat shrink those flanges onto the pipe, and then we apply a weld bead, and the combination of the weld and the heat shrink keeps that flange on the end of the pipe and complies with complies with the requirements of EN 545. So that's basically a flange joint, and we don't recommend that these are buried, or if they are buried, you have to mitigate any potential for angular deflection on them. So to give a quick overview of flange joints, they're rigid and they're self-anchoring. They don't have any flexibility. They're often used when you've got a pipeline design. They're often used with adjacent to a valve, for example. You might have a valve in a pipeline. You might have a flange socket and a flange spigot coming off either end. So you are incorporating flanges, but we'd always recommend you put a rocker pipe close to that so you don't impose any stresses onto those flange joints. It does withstand the pressure thrust. Standard pressure ratings for flanged pipes are PN10, PN16, PN25, which is 10 bar, 16, 25 bar. And I think the standards that you guys use over in Ireland are PN16, and that's the standard we supply from UK manufacturer, from our UK manufacturing perspective. The bending moments are limited by the sealing capacity of the joint and by the material strength. So a combination of flange bolts and gaskets indicate what that sealing capacity is. And again, we don't recommend you exceed those capacities, because flange joints, because they have no capability for flexibility, any loads that you impose upon them will be directed to the bolts or the flange itself, and possibly potentially overstress those. As I mentioned earlier, you've got to try and control bending moments to safe limits. So above ground, we recommend that you put these on plinths, or support them on hangers or whatever it might be. And then below ground, unless a flexible joint is located near to the flange joint, i.e. a flange socket or a flange spigot, flange pipes should not be buried. Now, It's quite a statement, that is. We often know that pipeline designs you have to bury flanges for some circumstances. If that's the case, we would recommend you put a rocker pipe in, or you put a flange section on a plinth, and where you move off a plinth to buried, you then put rocker pipes in there to accommodate any movement or flexibility. Because often, certainly again, when you're transitioning between materials, a challenge we often find is that if you're transitioning from a ductile iron section to let's say a polyethylene section, for example, and there's a stub flange of polyethylene and a flange of ductile iron, those are always the areas where you have to take extra care in terms of managing that transition, because they're the points at which those connections might fail. If they're going to fail, that's where they'll fail. So it's really important that care is taken on flanged sections and interface between different materials, which are flanges. So from a ductile iron perspective, from a flanges perspective, for potable water, gaskets are EPDM. For sewage systems, gaskets are nitrile rubber. There's an 80 international, what's that? I can't remember, the International Rubber Hardness Degrees, I think IRHD stands for, hardness of gasket. And there's a set of properties for the rubber that is in accordance with EN 681-1. So for flange joints, there's a number of guidelines to follow that we issue as part of our recommendations, but they're some of the principal examples of references that we use when we talk about flange joints. Again, flange joints, when you're bolting them together, we always recommend that you lubricate the nuts, bolts, and washers, and you use an environmentally what's the word I'm looking for, certified oil, and often, again, certainly from a UK perspective, there are RAS approved jointing systems you can use to put on nuts and bolts to lubricate them when you're jointing them. And the rationale for lubricating them is that you can then transfer the torque, the load when you're torquing the bolts to the sealing face, rather than the torque to overcoming putting the nut on the bolt. So that's why we suggest you lubricate the bolts. Oops. I lost my cursor there. We'd always recommend that you use the correct torque and a calibrated wrench, and you tighten bolts in the correct sequence. So flange joints are slightly different, potentially could be slightly more difficult to connect than push fit systems, because you have to follow a number of parameters. But that's an overview of flange joints as well. Now, for all those push fit joints that I talked about earlier, there's Saint-Gobain have a YouTube channel. So if you wanted to understand and see how those other joints are made, the push fit system, the standard VI, the universal VE, you can search for those, or I can send a link that you guys can have a look at if you want, that's got the Saint-Gobain YouTube channel, and it gives animations and illustrations of how those joints are made, which might be quite useful to I guess understand and overcome any questions you might have. So just in terms of Anchorage, we've got a piece of software we use called PipeSpec that we use to calculate Anchorage requirements. So basically, on the PipeSpec software that we have, it can do a number of things: hydraulics, part, full pipe. You can look at embedment requirements. There's an installed cost analysis you can do on that by putting your own numbers in. But that's a piece of software we've got that you can use for calculation, which I believe is downloadable from our website. So again, I can send you a link. For that. In terms of the parameters required for calculation, we need to understand the fitting details, the working pressure, the test pressure, what coatings there are on the pipes, depth of cover, width of trench, what the side fill materials are, excuse me, the height of the water table, for example. All those are parameters that we're interested in when we're trying to understand what the Anchorage requirements are. So all of the things we spoke about earlier about frictional resistance of soil, type of soil, water table, they manifest themselves in this information here, which is what we input into the calculation tool to give us some outcomes. So as a typical example here, on this particular example, from the drop-down menus, we've chosen a DN300 45-degree angle branch with a working pressure of 15 bar, test pressure of 20 bar, 2 meter depth of cover, and a water table at 1 meter. And we've chosen some different soil parameters. Native soil is described as clay. The backfill is poorly graded sand and gravel. and the pipeline is coated externally with what we call our TT coating, which is a thick extruded polyethylene coating on the outside of the pipe. So that's the parameters we put into the calculation, and that's what it gives us an outcome. The results of the calculation in this case suggest that anchorage will be required on both the angle angle branch pipeline and the main pipeline, and the anchorage can be achieved by using one of the different self-anchored systems that we spoke about earlier. But in this particular example here, when we talk about anchorage in main, we're talking about a length from the center of fittings of 24.3 meters, and the anchorage in the branch is a length measured from the center of fitting of 18.6 meters back down the branch. So you have to then calculate what that means in terms of number of joints. And if you're using a 6-meter pipe, you can build that in to say how many pipes do I need anchored joints in, how many joints for those pipes are going to be anchored, and then once you've gone beyond that 18.6 or that 24.3, you can just go back to standard push fit systems, because that thrust will dissipate over that length, so you're not then imposing that thrust further down the line. So that's basically the way the anchorage is calculated, and a tool that we have to do that. So as I mentioned, we've got some free software that you can download from the Saint-Gobain PAM website, and find that information on there. So to summarize, excuse me, thrust thrust can be developed within a pressurized ductile iron pipe system, and they need to be counteracted by anchorage. This anchorage can be in the form of concrete thrust blocks or self-anchored joints. And as I mentioned, the use of concrete does impose a lot of embodied carbon. So again, often these days, people are looking at alternatives to that, which is the anchored systems or the self-anchored joints that we can provide. Often they can be more cost effective and significantly reduce the carbon dioxide emissions. And another one of the benefits of anchored systems are that you can continue to lay. If you put an anchor gasket in a pipeline or a universal VE system in a pipeline, you can continue to lay. If you put a thrust block in, excuse me, often you have to wait for you have to build your shutter in, you have to pour your concrete, you have to wait for your concrete to go off before you then start laying or continuing to lay and testing against it. With anchored systems, you can continue to lay and test straight away. You don't have to wait for concrete to go off. You've not got that movement of concrete to and from the site as well. And I guess finally, the calculation of anchorage can be complex. But there is help in the form of a software package if you guys are interested. And I know Martin's worked with engineers in Ireland and Irish Water, where we've looked at projects where we've talked about some of the parameters we've discussed today. We've fed those parameters in, and we've been able to optimize designs around anchored systems using the understanding of the soil types, understanding of the pressure capabilities, and then applying our if you like, our knowledge to that scenario to define the optimum solution for anchorage. So that's me. Again, bit of a whistle-stop tour, as most of these presentations are. It's a bit of a whistle-stop tour at a headline level. We'd certainly welcome the opportunity to talk in more detail if you guys have got projects